This is the last module in this matrix chapter called quadratic form. Of course, this is an extension of the eigenvalue problem. Before that, I will explain what is meant by quadratic form. We have studied quadratic equation in 10th standard level. Quadratic means second degree. First, I will write certain expression in second degree. For example, x1 square plus 2x2 square plus x3 square minus 2x1 x2 plus 2x2 x3. There are three variables x1, x2, x3. Each term is second degree. So such an expression is called a quadratic form in three variables. Of course, you can even have x1, x3 term also. Just for example, I have written some expression. So this is a function of x1, x2, x3. Now, what we are going to study in this quadratic form, whether this value is always positive, whatever be the values of x1, x2, x3, whether it will be always negative, or for some set it is positive, for some set it is negative, for some set it is 0, like this. We want to check. If we have these cross terms, namely x1, x2, x3, x3, it is somewhat difficult to decide whether it will give always positive or always negative, like this. Whereas, if we have only these three terms, only square terms, for example, I consider only these three terms. Now the question is, will it be always positive? For x1 is equal to 0, x2 is equal to 0, x3 is equal to 0, it is always 0. So apart from x1 0, x2 0, x3 0, at least one of them should not be equal to 0. Now what you have to verify, just check whether for any set of non-zero values of x1, x2, x3, this is positive. The answer is yes. Whatever be the value you are giving, even if you give negative values, only real values you have to give. So this will be always positive. So this is called positive definite. Suppose you have another expression x1 square minus x2 square minus x3 square. Will it be always positive? Answer is no. When you take x1 is very large number and then x2 and x3 very small numbers, it will be positive. Whereas if you take, say, x1 is equal to 1, x2 is equal to 2, x3 is equal to minus 5. You substitute, simplify, you will get negative value for this expression. For some set it will be positive, for some set it will be negative. Such a thing is known as indefinite form. Therefore, our problem is to check whether you are having always positive definite or positive semi-definite. Semi-definite means it is 0 for at least one value and always otherwise it is positive. So the problem is to find the nature of this quadratic form. What we have to do, we have to make use of the concept of eigenvalue, eigenvectors. Now, what is the application of this quadratic form? So, in stability theory, all these things you will have some expressions to check whether the system is stable or not. Then we require the definiteness nature of this expression. Now, our problem is to check whether it is always positive definite or negative definite. So, I will give the definition of this, and before that, let us find the matrix form of this quadratic form. So we are going to write a matrix such that here some matrix, and here we are going to write x1, x2, x3, and here we write the transpose x1, x2, x3, and here we can write some matrix, so that when you simplify this matrix product, that should give this expression. There are infinitely many A's. So this quadratic form, so here I write this is x transpose into Ax in fact. So here what you have to do, the easy way, you write x1, x2, x3, and of course here x1, x2, x3, simply write x1 square term here, x2 2 square term here, and x3 square term here. That means x1 into x1 square, the coefficient of x1 square should be written here, coefficient of x2 square should be written here, and coefficient of x3 square should be written in this position. Now, the position what I am showing here, this is the position for x1, x2, and of course this is also for x1, x2 here. But what is the coefficient of x1, x2 here? That is minus 2. So the sum of these two numbers should become minus 2. Anything will give correct answer. However, we want to write A as a symmetric matrix. Therefore, you write equal numbers here so that the sum is minus 2. In other words, this minus 2 is divided by 2. You write minus 1 here, here also minus 1. So x1, x2 means first row, second position, the element should be minus 1, which is nothing but half of this coefficient. Similarly, what is the position here? First row, third column, that means x1, x3. But what about x1, x3 term? That is not there. Therefore, here you will have 0, here also you will have 0. And finally, this is the second row, third column position, that means x2, x3 coefficient. Sum of these two numbers should be equal to 2. So, we write equally 1 and 1 here. So, when you multiply this matrix with this column vector, and once again you will have this. You can just verify this. How do you verify? Usual multiplication, 1 into x1 minus 1 into x2 plus 0 into x3. Therefore, I am writing this as x1 minus x2. Then minus x1 plus 2x2 plus x3. Now third element 0, here x2 plus x3. Therefore, we have simplified this product in this form. Now this is x1, x2, x3. Now once again multiply this. You will have, this is in fact 1 row, 3 columns. This is 3 rows, 1 column. Therefore, this will be a 1 cross 1 matrix, simply one expression. Of course, that expression has more than one term, 5 terms will be there. So, row column wise once again you multiply. So, x1 into x1 minus x2. On expansion, what you will have? x1 square minus x1 x2. Just check, x1 into this. Then plus x2 into this. So, minus x2 x1 plus 2x2 square plus you will have x2 into x3, that is equal to x2 x3. And finally, this you have to multiply this into this, we have multiplied. Finally, x3 into this, that is equal to another x3 x2 plus x3 square. Just verify this into this plus this into this plus this into this. So, I have written all the terms, simplify, check whether you are having this. So, x1 square, then you are having 2x2 square, then x3 square. Then x1 x2 term, here minus x1 x2, another minus x1 x2 that you are having here. And finally, x2 x3 plus another x2 x3 this. Therefore, the quadratic form is written in the matrix representation. So, the first question is, whenever they give the quadratic form, they will ask how to find the matrix of the quadratic form. So, this matrix A is called the matrix of the quadratic form. Now, what is the application? We have to check whether this quadratic form is always positive or always negative, or whether it is positive for some values and negative for some values. For that, if you have cross terms, somewhat it is difficult. That is why what we are going to do, after writing the matrix of the quadratic form, we are going to find the eigenvalues, eigenvectors of this matrix. From that we can come to the conclusion. Now I am going to tell one important result regarding the nature of the quadratic form. So, first I will explain the definition of the quadratic form here. So, x transpose Ax is called quadratic form. It is, if it is always positive for all x not equal to 0, we say it is positive definite. Then number 2, if x transpose Ax, if it is greater than or equal to 0 for all x not equal to 0 and it is 0 for at least one x vector which is of course not 0, then it is called positive semi-definite. Similarly, if x transpose Ax is less than 0 for all x not equal to 0 then we say it is negative definite. Then fourth one, if x transpose Ax is less than or equal to 0 for all x not equal to 0 and equal to 0 for at least one x other than 0, then we say it is negative semi-definite. Then finally, if it is not satisfying any one of these four, we say that is otherwise we call the quadratic form as indefinite. Indefinite means for some set of values of x it is positive, for some set of values it is negative. Therefore, this is the nature of the quadratic form. So, what is our main problem in this module 3? They will give you a quadratic form. They will ask what is the nature of the quadratic form, then how will you transform this to canonical form. Canonical form means a form in which you are having only square terms like this. There will not be any cross terms like x1, x2, x2, x3 and so on. So, I am going to take two problems. For each problem, I will explain how to find the quadratic, that is canonical form of this quadratic form. First, we will consider this problem itself, how to find the canonical form for this and what is the application of the canonical form. So, step number 1, we find the matrix of the quadratic form. Just now I explained. So, the matrix is A is equal to, you write 1, 2, 1, which are the coefficients of x1 square, x2 square, x3 square. Here x1, x2 half of the coefficient, here also half of the coefficient. Then x1, x3 is missing, that is 0, here also 0. Then x2, x3 is 2, here half of this 1 and 1. So, this is step number 1. Then step number 2, find the eigenvalues, eigenvectors as we have studied in module 1. How will you find the eigenvalues, eigenvectors? You write the characteristic equation. Characteristic equation is lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. So, I explained how to find s1, s2, s3. s1 is 1 plus 2 plus 1, that is equal to 4. So, lambda cube minus 4 lambda square plus s2 means sum of the 2 cross 2 determinants, what I explained here. So, now we find S2, of course x2 is sum of the 2 cross 2 determinants obtained by deleting third row, third column, second row, second column, first row, first column, the usual manner. By deleting first row, first column, 2, 1, 1, 1 plus deleting second row, second column, 1, 0, 0, 1, deleting third row, third column, 1, minus 1, minus 1, 2. So, on simplification 2 minus 1, that is 1, plus here 1 minus 0, another 1, plus once again 2 minus 1, another 1, that is equal to 3. Now, S3 we have to calculate. We know that S3 is nothing but the determinant 1 minus 1 0 minus 1 2 1 0 1 1. So, it is equal to 1 into this product minus this product, that is 1. Then you have to change the sign. So, plus 1 into minus 1 minus 0. Of course, that next one is 0. So, this reduces to 0. Now, we got the values for S1, S2, S3. So, we substitute these values for S1, S2, S3 in the characteristic equation formula. So, we got the characteristic equation as lambda cube minus 4 lambda square, then plus S2 lambda, that is plus 3 lambda is equal to 0 because S3 term is 0. Now, what we have to do? We have to solve this equation. It is as simple as we have studied in first module, the problem. So, we take lambda as a common factor. So, the remaining lambda square minus 4 lambda plus 3 is equal to 0. So, it is very easy for you to factorize. So, this implies lambda into lambda minus 1 into lambda minus 3 is equal to 0. So, we got the eigenvalues as 0, 1, 3. You can verify whether we have done correctly or not. The sum of the three numbers should be equal to S1. So 0 plus 1 plus 3, that is 4, that is same as S1. The sum of the products taken two at a time, that means 0 into 1, that is 0, plus 1 into 3, that is 3, plus 3 into 0, that is 0, therefore that is 3, that is equal to S2. Then the product of these three numbers is S3. Therefore the eigenvalues are 0, 1, 3. So these are the eigenvalues for the matrix of the quadratic form. Once you find the eigenvalues, we can come to the conclusion about the nature of the quadratic form. I explained the definition of quadratic form earlier. Now I will tell the result regarding the nature of the quadratic form based on the eigenvalues. So these are the very interesting and important results. Number 1, if all the eigenvalues are positive, that means greater than 0, then the nature of the form is positive definite. Then number 2, if all eigenvalues are greater than or equal to 0 and at least one eigenvalue equal to 0, positive semi-definite. That is the case with our problem that we are dealing now. Just now we have seen the eigenvalues are 0, 1, 3. All are greater than or equal to 0 and at least one of the eigenvalues is 0. Therefore, for this problem, the nature is positive semi-definite based on this result. Now, the third conclusion, if all eigenvalues are less than 0, then it is negative definite. The fourth one, if all eigenvalues are less than or equal to 0 and at least one eigenvalue is equal to 0, then it is negative semi-definite. Now the last one, otherwise if it is not belonging to any one of these four categories, in other words you have positive as well as negative eigenvalues, it is indefinite. So using the definition, it is somewhat difficult to conclude what is the nature, because for the set of values of x1, x2, x3 you are choosing, you may get always positive, but there may be some other set for which it will be negative. But once you find the eigenvalues, it can be easily concluded about the nature of the quadratic form, because once you know the eigenvalues, it will fall into any one of these five categories, so that you can come to the conclusion regarding the nature of the quadratic form. Now, one more thing regarding this problem, what is the transformation, what is the actual meaning of the canonical form of all these things. So we got the eigenvalues for the matrix of the quadratic form in this problem as 0, 1 and 3. So 0, 1 and 3. So what we are going to write this expression as sum of three terms involving only square terms. So the canonical form, I am going to write so many results regarding this problem. Canonical form means standard form. Standard form means the form in which you are having only square terms. The answer is, you multiply this eigenvalue with y1 square, that is 0 into y1 square, then 1 into y2 square plus 3 into y3 square. Of course, the order is immaterial. You can even have the eigenvalues 3, 1, 0. In that case, you will write 3y1 square plus 1 into y2 square plus 0 into y3 square. So for this order, the quadratic form, the canonical form of the quadratic form is equal to y2 square plus 3y3 square. Then the nature means whether it is positive definite or semi-definite, all these things, since all the eigenvalues are greater than or equal to 0 and at least one of the eigenvalues is 0, it is positive semi-definite. Then the third one, there are certain terms like rank of the quadratic form, signature of the quadratic form, index of the quadratic form, all these things. So I will simply define rank is equal to number of non-zero eigenvalues. So how many eigenvalues are there which are not 0? You are having two eigenvalues which are not 0. Therefore, the rank of the matrix is the number of non-zero eigenvalues, that is equal to 2. Then number 4, index. Index of the quadratic form is equal to number of positive eigenvalues. Here there are 2 positive eigenvalues, therefore the index of this quadratic form is 2. And finally, there is one more thing called signature. Signature is defined as number of positive eigenvalues minus number of negative eigenvalues. Say here there is no negative eigenvalue, there are only 2 positive eigenvalues, therefore this is 2 minus 0, that is also 2 like this. So these are the definition of rank, index, signature. So rank means number of non-zero eigenvalues, index means number of positive eigenvalues, signature means number of positive eigenvalues minus number of negative eigenvalues. So I have defined all these things. Finally, one more thing regarding this problem. What is the transformation? What is the actual relationship between the given expression and the expression what we got as y2 square plus 3y3 square? That I will explain this. Then we will take one more problem regarding this. That is the most important problem in this matrix chapter. So first I will explain what is the transformation matrix. So what is the meaning of this? The given quadratic form is this. That is in matrix form x transpose Ax. And here this is written as y2 square 3y3 square, the diagonal form here. So we are having some relationship. The relationship is x is equal to my. Now what is the meaning of x is equal to my? X stands for x1, x2, x3, the column vector whose elements are the variables. M stands for the normalized modal matrix, and that I am going to define what is that. Before that I will write what is y. Y is y1, y2, y3. So the problem is how to find this m. I will explain systematically how to find the m, so that you will understand what is the relationship between the given quadratic form and the canonical form y2 square plus 3y3 square. So for that, what you have to do, we had to find the eigenvectors. Once again, that's a problem here. So remember the matrix of the quadratic form we got here 1, 2, 1, here minus 1, minus 1, here 0, 0, here 1, 1 I explained. Then we got the eigenvalues as 0, 1, 3. Now the remaining problem is to find the eigenvectors. So eigenvectors I explained in the first module. So I will explain how to find the eigenvectors very quickly, because you know the method. Case 1, lambda is equal to 0. So we have to find the eigenvector corresponding to lambda is equal to 0. For that we have to subtract 0 from the leading diagonal elements. So first equation 1 minus 0, that is 1, therefore x1 minus x2 plus 0 x3 is equal to 0. The second equation minus x1, then plus 2 minus 0, that is 2 itself, therefore 2x2, then plus x3 is equal to 0. Therefore by applying cross multiplication rule, as I explained in the first module, we are having x1 divided by this product minus 1 minus 0, therefore minus 1, then minus of this product is 1 minus 0, that is this one, then this product 2 minus 1, so that is 1. So we are having that x1 divided by minus 1 is equal to x2 divided by minus 1 is equal to x3 divided by 1. So we can have the eigenvector as minus 1, minus 1, 1. We can even change the sign also. We can even write 1, 1, minus 1 also. Any form is correct. Therefore, we got the eigenvector as minus 1, minus 1, 1. Now we go to the second case, case 2, that is to find the eigenvector corresponding to lambda is equal to 1. So subtract 1 from the leading diagonal elements. So 0 x1 minus x2 plus 0 x3 is equal to 0, minus x1 plus 2 minus 1, that is 1 here, so plus x2 plus x3 is equal to 0. These two equations are different, that's why we proceed to find the eigenvector using the cross multiplication rule. So this product is minus 1, this is 0, therefore minus 1, then minus of, this product is 0, this is also 0, therefore 0, then here this product is 0, minus 1, so minus 1. So we can have the eigenvector as x is equal to minus 1, 0, minus 1. We can even change the sign also, so 1, 0, 1. Now the last case, that is eigenvalue corresponding to eigenvector corresponding to 3. So case 3, lambda is equal to 3. Now what we have to do, we have to subtract 3 from the leading diagonal elements. 1 minus 3, that's equal to minus 2, so minus 2x1 minus x2 plus 0x3 is equal to 0. Then here minus x1, 2 minus 3, so minus x2 plus x3 is equal to 0. So we got x1 divided by this product, that is minus 1, is equal to x2 divided by minus of minus 2 plus 0, so minus 2. Then x3 divided by this product is 2 minus 1, that's equal to 1. So we can write the third eigenvector as x is equal to minus 1, 2, 1. So we got case 1, case 2, case 3. These are the three eigenvectors. So these are the eigenvectors corresponding to 0, 1 and then 3. Now as I explained, we can form the matrix P whose columns are these eigenvectors in that order. So we write P is equal to, that is called the model matrix, whose columns are the eigenvectors minus 1, minus 1, 1. Then 1, 0, 1. Minus 1, 2, 1. So this is called the model matrix. Now after getting the model matrix, we have to get what is so called normalized model matrix. Normalized model matrix means we write M is equal to, you divide each column by the length of the vector. You have studied in plus 2 level how to find the length of the vector. Simply square and add, take square root. So 1 plus 1 plus 1, when you square adding 3. So divide by root 3 each one of these elements. So minus 1 by root 3, minus 1 by root 3, 1 by root 3. So how do you get this? You divide each one of the elements of first column by square root of this square plus this square plus this square. Similarly, the second one, when you square and add, you are having 1 plus 0 plus 1, that is 2, taking square root, root 2. So 1 by root 2, 0, 1 by root 2. And the third one, when you square and add, 1 plus 4 plus 1, that is equal to 6, therefore divide by root 6. So minus 1 by root 6, 2 by root 6, 1 by root 6. So this is called the model matrix. So finally, the relationship between the given quadratic form and the canonical form is given by the transformation x is equal to my. Now what is the meaning? x1, x2, x3 is equal to this. You copy that, minus 1 by root 3, minus 1 by root 3, 1 by root 3, here 1 by root 2, 0, 1 by root 2, minus 1 by root 6, 2 by root 6, 1 by root 6, multiplied by y. Y stands for y1, y2, y3. So therefore this is the transformation. If we want to write the transformation in the expanded form, what we have to do that? Simply do one matrix multiplication. That means x1 is equal to this product, x2 is equal to this product, x3 is equal to this. So I will write in the expanded form. So x1 is minus 1 by root 3 y1, then plus 1 by root 2 y2 minus 1 by root 6 y3. How do we get? Usual row column multiplication. This into y1 plus this into y2 plus this into y3. Similarly, x2 is equal to minus 1 by root 3 y1, of course 0 next term, then plus 2 by root 6 y3, then x3 is equal to 1 by root 3 y1 plus 1 by root 2 y2 plus 1 by root 6 y3. So, if you have a lot of patience, what you can do, you substitute x1, x2, x3 in the given expression, simplify, and that will finally give you the simplified form, namely y2 square plus 3 y3 square, which is called the canonical form. Therefore, if they ask what is the transformation, then x is equal to my, where m is the model matrix. So, this is the answer. So, what we have done, the given quadratic form is x transpose x. What is the transformation? My. So, therefore, this is my transpose A, and then here once again my. So, this can be written as y transpose into m transpose am into y, and this m transpose am is nothing but the diagonal matrix whose diagonal elements are the eigenvalues 0, 1, 3, and y is this. That is why this is y transpose means what? y1, y2, y3. Then this is 0, 1, 3, 0, 0, 0, 0, all these things, and this is y1, y2, y3. So, on expansion you will get y2 square plus 3y3 square, and that gives the proof of this quadratic form. So, finally one more question they will ask in this problem. So, what is the main problem? They will ask reduce to canonical form. Step number 1, write the matrix of the quadratic form. Step number 2, find the eigenvalues, eigenvectors. Step number 3, find the model matrix, normalized model matrix. Final step, x is equal to my is the transformation, and the canonical form is this. Now, one more question they will ask. Since one of the eigenvalues is 0 and all other eigenvalues are positive, we concluded it is positive semi-definite. That means what? For at least one set of values of x1, x2, x3, that should give 0. Therefore, they will ask the question, give a set of values of x1, x2, x3, which will give the value 0. For that, the easy answer is, corresponding to lambda is equal to 0, what is the eigenvector we got? We got the eigenvector as -1, -1, 1, remember. So, if you substitute x1 is equal to -1, x2 is equal to -1, and x3 is equal to 1, which are the components of the eigenvector corresponding to 0 eigenvalue. When you substitute this in the real given quadratic form, that will give 0. So, therefore, the answer is x1 is equal to -1, x2 is equal to -1, x3 is equal to 1, which are the components of the eigenvector corresponding to lambda is equal to 0. Only when lambda is equal to 0, they will ask such a question. Find a set of values of x1, x2, x3, at least one of them is not 0, so that the quadratic form reduces to 0 here. You can just check up. When you substitute these values, what you will get? x1 square 1 plus 2 into x2 square. So, plus 2 plus x3 square, another 1, minus 2 x1 x2, that is minus 2 into this, so that is equal to minus 2, plus 2 x2 x3 here, so plus 2 into x2 x3. So, in this case what you are having, minus 2 into this, correct. Then here x2 into x2 x3, so minus, so plus 2 into this means another 2, just check. 2 into -1 minus 1 plus 1, that is equal to minus 2. So, on simplification it gives 0. Therefore, this completes the problem. So, the problem is they will give you a quadratic form, they will ask how to reduce the canonical form, and they will ask write a set of values of x1, x2, x3 which will give 0, and that type of question they will ask only when it is positive semi-definite or negative semi-definite. In other words, one of the eigenvalues should be 0. So, finally, I will take one more problem to explain how to bring to canonical form. This is the most important problem in the entire matrix chapter, I can even claim. So, the problem is reduce the following quadratic form to canonical form and find the nature, signature, rank, index, so many things will be asked. So, the given question is, the quadratic form is 6x square plus 3y square plus 3z square minus 4xy minus 2yz plus 4 zx. The question is reduced to canonical form, find the nature, then rank, index, signature, etc. So as I explained in the previous problem, step number 1, we have to write the matrix of the quadratic form. So it's very easy. Here instead of x1, x2, x3 it is given x, y, z. Therefore what we can do, we can write here x, y, z for convenience, so that you can write quickly what is the matrix of the quadratic form. This position is for x square term, so that is 6. This position is for y square term, that is 3. And this position is for z square term, that is also 3. The coefficients of x square, y square, z square I have copied. Then here this is the coefficient of xy, here also xy, therefore xy term is minus 4, equally share among these two places, minus 2, minus 2. Then this is for x into z, xz term is 4, so therefore if you equally divide 4, 2 and 2. And finally for yz, here minus 2 yz, therefore minus 1, minus 1. So step number 1 is over, which is to write the matrix of the quadratic form that you have written. Then step number 2, as I explained in first module, we have to find the eigenvalues and eigenvectors. So what is the characteristic equation? Lambda cube minus, you have to add these three, that is S1, anyway I will write systematically, S1 lambda square, S2 lambda minus S3 is equal to 0. What is S1? S1 is 6 plus 3 plus 3, which is the sum of the leading diagonal elements, that is equal to 12. Then what is S2? Sum of the 2 cross 2 principal minus, that means deleting first row first column, 3 minus 1 minus 1 3, deleting second row second column, that is 6 2 2 3, then deleting third row third column, that is 6 minus 2 minus 2 3. Just expand and simplify this. 9 minus 1, that is 8, 18 minus 4, 14, 18 minus another 4, 14. So you are having 28 plus 8, 36, and S3, the determinant itself, 6 minus 2, 2, minus 2, 3 minus 1, 2 minus 1, 3. So just expand this in the usual manner. So 6 into 9 minus 1, 8, then plus 2 into minus 6 plus 2, that is minus 4, plus 2 into 2 minus 6, that is equal to minus 4. So what do you get? 48 minus 8 minus 8, that is equal to 32. So we got S1, S2, S3. Substitute for S1, S2, S3 here. Then you will get the characteristic equation as lambda cube minus 12 lambda square plus 36 lambda minus 32 is equal to 0. Say we have done two problems in 3 cross 3 to find the eigenvalues, eigenvectors, but in both cases we got the constant term, namely S3 term as 0 here, but this is a problem in which that is not 0. So it is somewhat difficult to factorize. So what we have to do, we can solve this equation by trial and error method. Of course in calculator the facility is there to find the roots of the cubic equation. Those who know how to find the roots of the cubic equation using calculator, you can get those values to know the answer. Anyway you have to write all the steps. So step number 1, you find some value of lambda satisfying this equation by trial and error. You see the constant term minus 32. So you try for the values of which are the factors or divisors of this 32. If you have positive and negative terms, better you can try for positive values of lambda. If all the terms are positive, don't try for positive value because that will not give 0. You have to try for negative values. So in this case, the factors of 32 are 1, 2, etc. When you substitute lambda is equal to 1, 1 minus 12 plus 36 minus 32, of course that is not 0. Therefore lambda is equal to 1 is not a factor. Now you put lambda is equal to 2, check whether it is satisfied. When you try for lambda is equal to 2, this gives lambda is equal to 2 implies 8 minus 12 into 4, that is equal to 48, plus 36 into 2, that is 72, minus 32. Simplify, 72 plus 8, that is 80. 48 plus 32, another 80. That means this becomes 0. So we are lucky to decide one number now, the root of this equation. One of the roots of the equation is lambda is equal to 2. Therefore, use the so-called synthetic division. I mentioned in the first module what is called synthetic division, that I am explaining with reference to this problem. So just to write the 2 here, what we got which is satisfying the equation, copy this number, multiply, add, once again multiply, minus 20. This minus 10 into 2, that is minus 20. Once again add 16. 16 into 2, that is 32. So finally this number should give 0. If it is not giving 0, that means either you have concluded wrongly, lambda is equal to 2 is a root, or you have done some mistake here. So the given equation, namely the characteristic equation, is factorized as lambda minus 2 into lambda square minus 10 lambda plus 16 is equal to 0. So we get lambda minus 2. Now it is easy for you to factorize. This is lambda minus 2 into lambda minus 8 is equal to 0. So we come to the conclusion that the eigenvalues are 2, 2, 8. So first phase of this problem is over. So to reduce the canonical form, what we have to do, we had to find the matrix of the quadratic form, find the eigenvalues. Now here itself we can tell something about the nature of the quadratic form, index, rank, so many things. Now what is the canonical form? Canonical form is 2y1 square plus 2y2 square plus 8y3 square. Multiply the eigenvalues by y1 square, y2 square, y3 square, over. Next one is the nature of the quadratic form. Now what is the nature? Since all the eigenvalues are positive, that is positive definite, over. Then third one, the rank of the matrix. Now what is the rank of the matrix? I told you rank of the matrix is number of non-zero eigenvalues. All the eigenvalues are non-zero. So rank is equal to 3 because there are 3 non-zero eigenvalues. Next one is called index. What is meant by index? Index is number of positive eigenvalues, all are positive, therefore that is also 3. Then signature. What is signature? Signature means number of positive eigenvalues minus number of negative eigenvalues. There is no negative eigenvalue, that is 0 here. So 3 minus 0, that is also 3, over. Now what is remaining? We had to find the transformation. That takes some extra time to find the transformation. So that is the main thing to learn in this problem, how to find the transformation matrix. So that I am going to explain. For that we had to find the eigenvectors of this matrix. So we have put so many questions in the beginning. Can we have 2 independent eigenvectors for a single eigenvalue? Of course it is true, that I am going to explain. So corresponding to lambda is equal to 2, how to find the eigenvectors, corresponding to lambda is equal to 8, how to find the eigenvector, all these things I am going to explain this, and that will give the matrix of the quadratic form. So that will give the, say, model matrix, all these things, that will come to the conclusion here. So try to understand carefully. So whatever be the order doesn't matter. I consider the case 1, lambda is equal to 8, because it is very simple. So in that case, remember, I have to write the matrix. The matrix is 6, here 3, here also 3, and here minus 2, here also minus 2. Here you are having 2, here also 2 excess term, here minus 1, minus 1. So this is the matrix A. So how will you find the eigenvector? So we have studied for 2 or 3 problems. Subtract 8 from the leading diagonal elements. So 6 minus 8 minus 2x1 minus 2x2 plus 2x3 is equal to 0. Then second equation, minus 2x1, here 3 minus 8, that is equal to minus 5x2, then minus x3 is equal to 0. So these 2 equations are different. Apply cross multiplication rule. So x1 divided by this product minus this product, here 2 minus of minus 10, that is plus 10, therefore 2 plus 10, that is equal to 12. is equal to x2 divided by minus of, this product is 2, minus of minus 4. So, what you are having 2 plus 4 6. So, you are having minus 6, and finally x3 divided by this product, that is 10 minus 4, that is 6. So, 6 is a common factor, therefore, we can write the eigenvector as, so x1 divided by 2 is equal to x2 divided by minus 1 is equal to x3 divided by 1. Therefore, we can write the eigenvector as 2 minus 1 1. So, this is the first eigenvector corresponding to lambda is equal to 8. Of course, there is only one independent eigenvector. Now, we come to the case 2. There are only two cases, remember, because there are only two distinct eigenvalues. So, this is the most important thing in the entire matrix chapter. I can tell you how to find the eigenvectors corresponding to lambda is equal to 2. So, I will explain patiently just to see that. So, case 2, lambda is equal to 2. Subtract 2 from this leading diagonal element. So, you are having that Ax is equal to lambda x gives 4x1 minus 2x2 plus 2x3 is equal to 0. Now, what about the next equation? Minus 2x1, you have to subtract 2 from this, plus x2, then minus x3 is equal to 0. So, in the module 1 I told you, if the first and second equation are same, then necessarily you have to write the third equation. These two equations are same. How? Because the ratios are equal, you see that 4 by minus 2, that is minus 2, minus 2 by 1, that is also minus 2, 2 by minus 1, that is also minus 2. Therefore, these two equations are one and the same. In other words, the second equation is obtained by dividing the first equation by minus 2. So, necessarily we have to write the third equation. We are forced to write the third equation. So, when you write the third equation here, 2x1 minus x2, when you subtract 2 from these 3 minus 2, that is plus x3 is equal to 0. And this equation is also same as the first two equations, because this is nothing but negative of this. Multiply both sides by minus sign, second equation, you are having this. Suppose this equation is independent of this separate equation, then you can apply cross multiplication rule. In that case, there is only one eigenvector corresponding to lambda is equal to 2. In that case, we cannot diagonalize at all. But anyway, that does not happen in this problem. We are having all the three equations same. So, we cannot apply cross multiplication rule. Then what you have to do? That I am explaining. Since we are having only one equation, we have to find the set of values of x1, x2, x3 satisfying this equation. There are so many ways of fixing the values. Two values you can fix, you can find the third value. Of course, you should not fix the values x1 is equal to 0, x2 is equal to 0, because in that case x3 will become 0. Therefore, at least one of the two values should not be equal to 0 when you fix. So, as a convention, what do? We fix one value as 1. For example, I fix x1 is equal to 1. Now, fix x2 is equal to 0. Now, you find the value of x3, substituting. All the three equations are one and the same, remember. Therefore, any one of the three equations you can take. So, when you fix x1 is 1, this becomes 4 minus 0 plus 2x3 is equal to 0. Therefore, this implies x3 is equal to minus 2. So, we got another eigenvector 1 0 minus 2. Now, the question is, we have to diagonalize using orthogonal transformation they will give. Therefore, we have to find the third eigenvector in such a way that that vector is orthogonal to each one of the eigenvectors, particularly for that 1 0 minus 2 here. Now, I am explaining something, you try to learn that. Say, to find another eigenvector, there are so many ways. Instead of fixing 1 and 0, you fix 0 and 1. For example, if you fix 0 and 1, what will you have? When you put x1 is 0, x2 is 1, then x3 becomes 1. So, see that 0 minus 2 plus 2. Therefore, 0 1 1 is also an eigenvector, but is it orthogonal to this vector what you got for lambda is equal to 2? Orthogonal means the dot product should be 0. So, 0 into 1 plus 1 into 0 plus 1 into minus 2, that is not 0. Even though it is an eigenvector, that is not orthogonal to this vector. But this vector will be orthogonal to this, you can check, because 0 into 2 plus 1 into minus 1 plus 1 into 1, that is equal to 0. So, even though this is an eigenvector corresponding to lambda is equal to 2, this is not orthogonal to the vector what you got earlier. Therefore, our problem is to find another eigenvector which is orthogonal to this. So, there are two methods for that. So, the simple method I am telling, the simple method is you fix 1 and 0, you got this value as minus 2. Now, what do we do? Other than the 0, you are having these two numbers here. One of them may be 0 of course, but anyway here they are not 0. You just interchange these two values. That means you fix x1 is equal to minus 2 and x3 is equal to 1. But you have to change the sign for one of the things. In other words, what I am telling, here you write minus 2 and then 1, you change the sign Sign for one of the two numbers. That means you fix x1 is equal to 2 and x3 is equal to 1. So, once again I will explain, interchange these two numbers other than 0, that means minus 2 and 1, and change the sign for one of the two numbers. That means I am changing minus as plus, therefore 2, 1. Now, once you fix these values, get the value of x2 from this equation. So, how will you get? Either you can take this equation or these all are same of course. So, x1 is 2 here, that means 2 into 2 4 minus x2 we have to find plus this x3. x3 is equal to 1 here, so is equal to 0, therefore x2 is equal to 5. Therefore, we got the eigenvector as 2, 5, 1. So, another eigenvector I got 2, 5, 1. So, that is an eigenvector. So, how to check whether this is an eigenvector? This equation should be satisfied, that is all over. So, when you substitute x1 is equal to 5, x1 is equal to 2, x2 is equal to 5, x3 is equal to 1, just check. 4 into 2, 8, minus 10 plus 2, that is equal to 0. Therefore, naturally this is an eigenvector corresponding to lambda is equal to 2. Then one more checking you can do that. After getting the eigenvector in this manner, now check whether this eigenvector is orthogonal to this as well as this. So, definitely that will be so. Only because of to get orthogonality we have done this technique, interchange, change the sign one of them, substitute for x1, x3, get the value of x2, I got this. Now, you see the dot product, this into this 2, here 0, here minus 2. So, whatever be the value of this you are going to obtain when you multiply by 0, that will give 0. That is why we have done this technique. So, finally, I will write the three eigenvectors. First eigenvector is 2 minus 1 1, next eigenvector 1 0 minus 2, the third eigenvector 2 5 1. So, do not think that this is the only way, there are so many ways. For example, instead of fixing 1 0 here, if you fix 0 1, then corresponding to that we have to apply the technique of finding the eigenvector. Finally, we have to find three eigenvectors and they should be orthogonal. And the difficulty is only in finding the eigenvectors corresponding to the repeated eigenvalue. Now, finally, just check. The dot product for each one of these will be 0. So, 2 plus 0 minus 2 0, 2 plus 0 minus 2 0, even for this 4 minus 5 plus 1 0. Therefore, we got this matrix which is called the model matrix. Then as I explained in the last problem, the normalized model matrix is obtained simply by dividing each one of the eigenvectors by the corresponding lengths. That means here 4 plus 1 plus 1, that is 6. So, divide by root 6. Therefore, 2 divided by root 6 minus 1 divided by root 6, 1 divided by root 6. Then here 1 plus 0 plus 4, that is 5. Therefore, 1 by root 5, 0 minus 2 by root 5. And finally, here 4 plus 25, 29 plus 1, 30. So, 2 by root 30, 5 by root 30, 1 by root 30. So, this is called the model matrix. But remember, model matrix need not be unique. Depending upon the way in which you have arrived at the eigenvectors, corresponding to that you can get the model matrix and normalized model matrix. So, after getting M, finally we write the transformation. Now what is the transformation? X, Y, Z, these are the variables in the original quadratic form, that is equal to M, Y, Y in the sense Y1, Y2, Y3. So M is nothing but this matrix. So if you want to write the expanded form of the transformation, X is equal to this into Y1 plus this into Y2 plus this, therefore I can write in a expanded form 2 by root 6 Y1 plus 1 by root 5 Y2 plus 2 by root 30 Y3. Similarly, for completeness, anyway I will write that Y is equal to this into this, that means minus 1 by root 6 Y1 plus 5 by root 30 Y3, and X is equal to 1 by root 6 Y1 minus 2 by root 5 Y2 then plus 1 by root 3 Y3. Say once you substitute this x, y, z in the original quadratic form, then it will reduce to the canonical form. What is the canonical form? We got the canonical form as the eigenvalues 2 to 8 we have written. There were 2y1 square plus 2y2 square plus, so of course here one thing. Now what is the order in which we have written, that is very important here. Here we have written the first eigenvector as 8. The second eigenvector corresponding to 2, this is also 2 here. Therefore, in this case, it will reduce to the quadratic form, canonical form, 8y1 square plus 2y2 square plus 2y3 square. So, earlier I have written the answer in the canonical form as first 2y1 square plus 2y2 square plus 8y3 square. But for that you must write the model matrix in such a way that the columns corresponding to those order. But here if you write in this order, the canonical form will be this. Therefore, the main problem is how to find the canonical form. Just I explained. So finally I conclude this third module by telling the summary of this. So the problem is they will give you a quadratic form. They will ask you to reduce the canonical form using orthogonal transformation. Step number 1, you have to find the matrix of the quadratic form. The third one, so next step is find the eigenvalues, eigenvectors. Then find the nature depending upon this. If all the eigenvalues are positive, positive definite. If all the eigenvalues are negative, negative definite, and so on. Now finally I conclude with one more thing about the nature of the form. So tell the nature of the form, there is one easy method. First you write the matrix of the quadratic form 6, 3, 3, and here we wrote minus 2, remember. Here XZ form means here you are having 2, here also 2, here minus 1. So this is called the matrix of the quadratic form. So without finding the eigenvalues, eigenvectors also, you can come to the conclusion whether it is positive definite or negative definite. Other things, so there is some ambiguity. So what I am telling, just to find the leading minus. Leading minus means 1 cross 1 matrix determinant, then 2 cross 2 determinant formed by first 2 rows, first 2 columns, and 3 cross 3 determinant formed by first 3 rows, this one. So if all are positive, positive definite. If the sign about this D1, D2, D3, D1 stands for this determinant, D2 stands for this determinant, D3 stands for this determinant. If it is negative, positive, negative, in that alternate positive, negative, first starting with negative, negative definite. But of course, for other pattern that depends upon the problem, we cannot come to the conclusion. Now see that this is 6, 18 minus 4, that is equal to 14. Then this determinant 3 cross 3, that is equal to 32. All are positive, therefore positive definite. Therefore easy way to find the nature is just to form the matrix of the quadratic form, find the leading minus. If all are positive, positive definite. If it is negative, positive, negative, alternately negative definite. Otherwise it may be positive semi-definite or negative semi-definite, or it may be indefinite like this. So this is the summary of this quadratic form.